Jai Hind, dear children. Let us see some numericals today. In the following ray diagram are given position of an object O, image I, and two lenses L1 and L2. The focal length of L1 is also given. Find the focal length of L2. So in the ray diagram, a convex lens and concave lens is shown, and focal length of convex lens is given, that is f equal to 15 centimeter, and you want to find out the focal length of the concave lens L2. The object distance is given in the case of convex lens, that is 40 centimeter, and the separation between convex lens and the concave lens, that is 14 centimeter, and the image distance for concave lens, that is 30 centimeter. Here from the object, the ray of light incident on the convex lens, and after the refraction the image is formed at I, that is I dash. So I dash is the image formed by the convex lens. This image acts as a object for the concave lens. So that is a virtual object. So from the virtual object, the ray of light again incident on the concave lens, and the final image is formed at I, that is at a distance 30 centimeter from it. So we can consider two cases here. So in the first case, we can take the convex lens only. So in the case of convex lens, what is the object distance from the figure? That is u equal to minus 40 centimeter. Then what is the focal length of convex lens? That is f equal to plus 15 centimeter. Then using the thin lens formula, you should find out the image distance of convex lens. So what is the thin lens formula? 1 by f equal to 1 by v minus 1 by u. Then 1 by v equal to 1 by f plus 1 by u. Then we can substitute the values, that is 1 by 15, then u minus, so minus 1 by 40. So when you calculate these values, you will get the answer v equal to 24 centimeter. This is the image distance for the convex lens. Okay. That is the image distance for the convex lens, that is 24 centimeter. This image acts as a object for the concave lens. Now we want to find out the object distance for the concave lens. Here only the image distance is given in the case of the concave lens. Next we will write concave lens. So v is given, that is v equal to, that is plus 30 centimeter, that is positive sign, plus 30 centimeter. Then what is the object distance here? That is object distance u equal to, image distance for the convex lens is 24 centimeter, and the separation between the convex lens and the concave lens is 14 centimeter. So image distance of the convex lens minus this separation gives the object distance for the concave lens. So we can write here 24 minus 14, that is equal to 10 centimeter. So this is the virtual object, so we can write the object distance as positive value. So virtual object distance, that is u equal to plus 10 centimeter. Now we apply the thin lens formula, that is 1 by f equal to 1 by v minus 1 by u. That is 1 by f equal to, what is image distance? That is 1 by 30 minus 1 by 10. Therefore focal length of the concave lens, that is f equal to, after calculating all these values, you will get the answer f equal to minus 15 centimeter. So this is the focal length of the concave lens. Next question, find the position of the image formed by the lens combination given in the figure. So here Three lenses are given. Two is convex lens and the one is concave lens. An object is placed at a distance of 30 centimeter from the first lens and its focal length is 10 centimeter. And the second lens, concave lens, its focal length minus 10, and the third lens, convex lens, its focal length 30 centimeter. And separation between the first and the second lens, that is 5, and the second and the third lens, that is the 10 centimeter. So here the image formed by the first lens act as a object for the second lens, and the image formed by that lens act as a object for the third lens. Okay, so now we can find out, using this concept we can find out the position of the image. Now we consider the first lens. What is the object distance of the first lens? That is u equal to minus 30 centimeter, and its focal length is also given, that is 10 centimeter. Then you apply the thin lens formula for the first lens, that is 1 by f1 equal to 1 by v1 minus 1 by u1. So there 1 by v1 equal to 1 by f1 plus 1 by u1. Then substitute the values, 1 by 10 minus 1 by 30, that is v1 equal to 15 centimeter. So that is the image distance for the first lens, v1 equal to 15 centimeter. So that image acts as a object for the second lens. So what is the object distance for the second lens? Image distance of the first lens minus this separation. So 15 minus 5, that is equal to 10 centimeter is the object distance for the second lens. Now we can write the second lens. Okay. So for the second lens, what is the object distance? u2 equal to 15 minus 5, that is equal to 10 centimeter. It is the virtual object distance, so we can note it as plus 10 centimeter. Okay. Then what do you want to find out here? Image distance for the second lens. What is the focal length? f equal to minus 10. So here we can write f2 equal to minus 10 centimeter. Again we can apply the thin lens formula to find out the image distance. So 1 by v2 equal to 1 by f2 plus 1 by u2. So that is equal to 1 by minus 10 plus 1 by 10. Okay. So here then after the calculation we will get the answer v2 equal to infinity. So image distance for the second lens, v2 equal to infinity. Here the object, that means the object is at 10 centimeter, that is at the focus also 10 centimeter. So the object is at focus, so you should get the image at infinity. Clear? This image acts as a object for the third lens. So here for the third lens, okay, so we can write the third case. For the third lens, what is the focal length of the third lens? That is f equal to f3, okay, f3 equal to plus 30 centimeter. Then what is the object distance for the third lens? That is image distance for the second lens, that is infinity minus this separation, okay, infinity minus 10, that is also infinity. So we can write infinity. Again we can calculate the image distance, that is 1 by v3 equal to 1 by 30, that is 1 by f3, then plus 1 by infinity, that is v3 equal to 30 centimeter. So object is at infinity, then image is formed at the focus. What is the focus here? Focal length, that is the 30 centimeter. Clear? Next question. A converging lens of focal length 50 centimeter is placed coaxially in contact with another lens of unknown focal length. If the combination behaves like a diverging lens of focal length 50 centimeter, find the power and nature of the second lens. So here the question consists of converging lens of focal length 50 centimeter. So that we can note it as f1 equal to positive value, okay, converging lens, that is the convex lens, so plus 50 centimeter. Then is placed in contact with another lens of unknown focal length. So that you want to find out, that we can note it as f2. If the combination behave like a diverging lens of focal length, so that is concave lens. Combination act as a diverging lens, that we can note it as f equal to minus 50 centimeter because it is a concave lens. Then you can apply the lens combination formula, that is equivalent focal length of the combination of lenses 1 by f equal to 1 by f1 plus 1 by f2. So, we can find out the f2. So, 1 by f2 equal to 1 by f minus 1 by f1, then substitute the values 1 by minus 50 minus 1 by 50. Then after the calculation you will get f2 equal to minus 25 centimeter, then change it into meter, that is minus 0.25. It is negative value, minus 25 centimeter equal to minus 0.25 meter. So, the minus sign represents that the second lens is a diverging lens. Okay, that is the concave lens. Then what is the power of this lens? So, you want to apply the power formula P2 equal to 1 by F2, that is equal to 1 by minus 0.25. So, write it in diopter, that is P2 equal to minus 4 diopter. Clear? Next topic, total internal reflection. So, what do you mean by this internal reflection? If light passes from an optically denser medium to a rarer medium, then at the interface the light is partly reflected back to the denser medium and partly refracted into the rarer medium. This reflection is called the internal reflection. So, what is this total internal reflection? So, here the ray diagram shows that this is the denser medium, that is the water, and this is the rarer medium, that is the air. This is the water air interface. So, when a ray of light passes normally, then what is the angle of incidence and angle of refraction, that is angle I equal to angle R equal to 0. Suppose the ray of light incident at an angle of incidence I, then it refracted into the rarer medium at an angle of refraction R. Then when the angle of incidence increases, angle of refraction also increases. Then a stage is reached at which for a particular angle of incidence, angle of refraction becomes 90 degree, which means that the ray of light refracted along the water air interface. At this angle of incidence, at which the angle of refraction is 90 degree, then that angle of incidence is known as the critical angle of incidence, that is noted as I suffix C. Then when the angle of incidence is greater than this critical angle of incidence, all the ray totally reflected back to the denser medium. This phenomena is known as the total internal reflection. So, here once again when the angle of incidence increases, angle of refraction also increases. Then at a particular angle of incidence, angle of refraction becomes 90 degree. In that case, the refracted ray passes along the water air interface. That angle of incidence is known as the critical angle of incidence. Then again the angle of incidence increases, and if the angle of incidence greater than this critical angle of incidence, then all the ray reflected back to the denser medium. This phenomena is known as the total internal reflection. So, there are two conditions for the total internal reflection. So, the first condition, the ray of light must passes from denser medium to rarer medium. This is the first condition. Second condition, angle of incidence must be greater than the critical angle of incidence. These are the two conditions for the total internal reflection. First, light must passes from denser medium to rarer medium. Second, angle of incidence in the denser medium must be greater than the critical angle for the two media or critical angle of incidence. These are the two conditions for the total internal reflection. Clear?